Alrighty here, so it is 12, so we'll get started. On behalf of the Environmental Finance Center Network, welcome to our webinar today on operator certification, sedimentation, and wastewater treatment. My name is Maya Bani from the Syracuse University Environmental Finance Center. Just before we begin, we're going to go over a few housekeeping items and then we can get started. During the training today, everyone will be kept on mute to ensure audio quality. If you have a question, please type it into the GoToWebinar question dialog box anytime throughout the session. We will be saving your questions for a facilitated Q&A session at the end of the presentation. After the webinar, you will receive a follow-up email that includes a link to the recording and any other information you may need. You can also download the slides from today in the Handouts tab in your GoToWebinar control panel. This session has not been submitted for pre-approval of continuing education credits, but eligible attendees will receive a certificate of attendance for their personal record. To receive a certificate for this session, you must attend for the entire session and register and attend individually using your real name and unique email address. Certificates will be sent via email within 30 days of the webinar date, and if you have any other questions or need assistance, please contact smallsystems@syr.edu. Now for a little bit about us. The Environmental Finance Center Network provides training and technical assistance to small water and wastewater systems in all U.S. states and territories through our building technical, managerial, and finance capacity programs. If your community or utility needs assistance with drinking water or wastewater system management, please feel free to contact us through our request form, which I'll be sharing shortly in the chat. And on that note, we can get started. I would like to introduce our presenter for today, James Markham, a research engineer from the Southwest Environmental Finance Center.
Thanks, Maya. Thanks, everybody, for joining us today. Just got to get our screen switched here real quick. Make sure I'm showing the right window. All right. Again, thanks, everybody, for joining us for today, which is part of our ongoing operator certification series. Our goal with this webinar series is to really introduce those of you who are new to the wastewater world and maybe prepping for your first OpCert test, or those of you who have taken the test and maybe didn't quite get the results you're hoping for, to the various wastewater treatment concepts, processes, equipment, and math that you're going to be using through your career and on the test, and hopefully provide enough detail and refreshers for the old hands in the audience who might be going for a higher level of certification, or who maybe don't use every process we talk about in this series on the daily, but don't want to get rusty on the concepts in the math. That being said, these webinars are introductions. They should be used in addition to your other study resources. They are supplements, not substitutes for further study. Given the limited time we have, we can't fully explain everything in the depth that you're going to need to know it for your operator certification, but hopefully this will be a very useful introduction or refresher for the particular concepts that we're going to cover today. And today we'll go over some concepts, some theory, a little bit of math, and some examples related primarily to sedimentation. At its most basic form, this is just the settling of heavier particles in the wastewater stream out of the stream. The idea is if we put the effluent in a basin and slow it down enough, and maybe do some other engineering tricks, we can get it to a point where the wastewater won't transport the suspended material that we happen to be focusing on in a particular process, and gravity can do its work, pull it to the bottom of the channel, and we can remove it. The reason that this works is that the solids in wastewater typically have a specific gravity higher than 1. So remember, specific gravity is the weight of those particles in relation to an equal volume of water. Water has a specific gravity of 1, varies a little bit, but you can just use 1 as a standard. And if the specific gravity of a particle is higher than 1, given enough time and a slow enough flow velocity, it'll sink to the bottom. Particle shape, size, and water temperature can have an impact on that sinkage rate, and we'll talk a little bit about that as we go along. Another concept we'll discuss today is flocculation. which usually involves either mixing techniques and sometimes additives to promote the clumping together of smaller, lighter particles so that they fall out of suspension and or fall out of suspension quicker. Flocculants in relatively dilute solutions really don't behave like discrete particles, and instead they sort of coalesce, kind of like snow, as they fall through the wastewater toward the bottom. You know, they clump together, they gain mass, and as they gain mass, they settle faster. The extent to which that happens in a basin really depends on a lot of things, like opportunity for those particles to contact each other, which in turn depends on things like overflow rates, the depth of the basin, velocity gradients in the system, particle concentration, particle size. The effects of these variables will typically be determined by sedimentation tests, which are outside the scope of today's talk, but I believe we are going to be addressing when we do some session on lab work. Today we're going to be talking about sort of the physics and some of the clever engineering we use to facilitate and speed up sedimentation processes, and also to segment it so that we're separating out particular particulates, specific particulates in the basins that we want them to fall out on. We typically think of flocculation in terms of its impact on sedimentation processes, but it can also be used in processes that separate solids using skimming or filtering as well. The main takeaway with flocculation is that we're basically talking about getting small particles to clump together to form big particles that have slightly different physical properties, which we can then exploit for their removal from the wastewater stream. If you think about activated sludge processes, for example, there's a lot of microbes in there. Those have a natural tendency to flocculate and settle easily, which we can exploit when we're trying to remove them in secondary clarification, but which we're fighting in the activated sludge process in the tanks using agitation and aeration to keep everything in suspension. Basically, if you turn everything off in there, it's all going to settle to the bottom, but we can exploit that tendency as a treatment process. And then we'll touch lightly on flotation, which is of course the opposite of sedimentation. Here we're raising lighter materials to the top of the wastewater for removal, things like fat and oil and grease and hair and other things like plastic, things that are light. This can be done a lot of different ways with aeration, evolution of gas and water, chemicals, electrolysis, heat, bacterial decomposition will do it as well. You know, if you're wastewater goes septic, you can have things floating to the top that you don't want to. Some materials float by themselves given enough time. Fats, oils, and greases are in that category, which is why we typically have skimmers on the top of clarifiers so that we can capture those things that are sinking and those things that are floating. What those floating substances have in common is that they have a specific gravity less than 1. In other words, they're less dense than water, so they're buoyant and they float on top. And again, we'll kind of touch on flotation as it applies to different processes that we go through today, but the primary focus is going to be on sedimentation, and primarily in the preliminary and primary treatment stages, although we'll touch a little bit on secondary treatment as well. So the sedimentation principle is really used throughout the treatment train. In most cases, you know, the primary purpose is to produce a clarified, though not necessarily clear effluent, depending on where you are in the treatment process. And in many cases, to produce sludge that has a solids concentration that enables it to be easily handled and treated. If you were with us in our last session, which was an overview of preliminary treatment processes, you got a preview of sedimentation without the math that we're going to be doing when we discussed grit removal and some of the velocity-based methods that are used. For those of us who weren't with us in the last webinar, what you're looking at here is a couple of grit removal channels in a very simple small system, and the idea here is we slow the water down to about 1 foot per second, and that allows the grit, which has a specific gravity around 2.5, to relatively easily fall out of the wastewater stream, but keeps the lighter organics in the stream. Those are lighter, they have a much lower specific gravity, much closer to 1, typically in the just above 1 to maybe 1.25 range, and the size of that stuff can be really, really small, down into the micron ranges. So the time that it takes for settling to occur in primary and secondary treatment is typically a lot longer than in a preliminary treatment like grit removal. In grit removal, we're typically talking about, you know, detention times and settling times in the minutes, whereas in primary and secondary treatment, that can be in the hours. Another difference between grit settling and settling of particulates in later stages of treatment, primary and secondary treatment, are that in grit settling, we're talking about discrete particles. that don't really interact with each other. It's just they're big enough and heavy enough that gravity does its thing and they go straight to the bottom. Whereas with primary and secondary treatment, the particles are interacting with gravity, but also each other. So the physics and the math is a little bit different and a bit more complicated in those processes. As I said, we use this in primary treatment. Mostly what we're targeting in the primary treatment stages are TSS removal, total suspended solids. Tank shapes vary, but the principle is the same. We're using engineering and operation principles to give those particulates time to settle out in the tank so that they don't get pushed on to the next stage. We use them in secondary treatment as well. Here we're typically removing biological floc that's left over from the activated sludge process, and we might actually be removing chemical floc as well if we have a chemical coagulation process going on. And again, much slower detention times that we're talking about, and obviously we're going to be getting much clearer water. We talked about relative clarification. The water coming out of the secondary clarifier is going to be a lot clearer because it's basically ready for disinfection, potentially dechlorination and discharge. So you can actually think of the settling or the sedimentation process in a couple of different ways. There's actually several kinds of settling that are going on within the treatment plant, and gravity is obviously central to all of them, but with the smaller particles, we have to consider the interactions between the particles as well as gravity. So again, primary purpose of any settling process is to produce a clarified effluent and sludge that has a solids concentration that we can use it with, and how clear that effluent is going to be is going to depend on where in the treatment stages you are. So you can kind of condense gravitational settling or sedimentation into sort of four basic categories. There's discrete particle settling, flocculent settling, hindered settling, and compression settling. And that's kind of what this table lays out here. Discrete particle settling, that's the grit and sand removal. Those particles are big enough and heavy enough that they essentially settle out by gravity without really any significant interactions between the particles. Flocculent settling is a little bit different. It's typically used for solids removal in primary settling facilities, and this is what's going on in the sort of upper portions of secondary settling tanks. And this is basically dilute suspensions where smaller particles are banging into each other, conglomerating, getting bigger, and gaining mass and sinking down. Ballasted flocculation is essentially just helping that process along using inert agents and polymers to promote that settling. Hindered zone settling is typically what's going on sort of at the lower levels, the intermediate level of secondary facilities. It's where the concentrations are thick enough that the solids are kind of interacting with each other. And typically this is sort of like right at the interface between the liquids and the solids. Things are clumped together. They're not compacted, but they're clumped together so that we're essentially moving together as a mass. And then compression settling is what's going on underneath. It's where particles are so concentrated that the additional settling of additional solids above them is pressing them down and concentrating them. And that occurs basically at the lowest levels of secondary facilities or on the bottom of biosolids thickening facilities. We've got two other things on our list here. Accelerated gravity settling is using cyclones and things like that for the removal of grit particles, and then obviously flotation is rising everything to the top. So some sort of broad categories, but one way to kind of think about all of these is think about snow falling in a storm. If you've got a hailstorm, those are discrete particles. They essentially come straight down. They might be going diagonally because of the wind. You can think of the flocculent settling and the hindered settling and compression settling as kind of analogous to what's going on during a heavy snowfall. At upper levels, you've got discrete snow crystals. As they fall, they conglomerate together, so you get big flakes. They lay on the ground eventually, and sort of at the surface, you've got this sort of mushy conglomeration of flakes together. And then, of course, the more snow builds up, the more compressed the bottom layer gets as you go. So I think of that as kind of a useful analogy to sort of physically think of what's going on in that process. If you happen to have a snow globe at home, shake it up, watch what's happening. That'll give you kind of an idea of what's going on with flocculent settling. But as I said, we use settling throughout the process. I'm going to start with grit removal sedimentation, because that's kind of the easiest thing to model. So remember, grit is that heavy particulate matter. It's sand, eggshells, coffee, bone fragments like that. Typically what we're doing is reducing velocity so that those particles can settle out. If you were at the preliminary treatment webinar, you'll have seen some additional things that we can do. But for this simple example, we're just going to focus on reducing water velocity, letting those heavy particles settle out, and the lighter organic particles move on to the next treatment. And it just so happens that the ideal velocity for that is about 1 foot per second, although 0.8 to 1.3 foot range is typically acceptable. And this is what a grit channel more or less looks like in its simplest form. Basically, water is flowing left to right. We've got a couple of channels, so we can use one or more at any given time, and we slow the velocity down so that the grit can settle, and then we've got weirs at the end that the water flows out of. And again, really important, because in this particular process, we're targeting grit, that heavier specific gravity stuff. We want the organics to move along, because if things are going too fast, we're going to push that grit into our primary tanks, which we don't want, because that'll negatively impact our primary treatment stages. And if things are moving too slowly, organics will settle out in the grit, and then when we remove it, that'll continue to decompose, create odors, potentially attract vermin. So, this is all about sort of dialing in the appropriate velocities and depths for the particular constituent material that we're trying to remove. So now that we got a little bit of sort of overview and concept and theory down, let's look at a little basic math. Assume we're looking at this grit channel, and for some reason, we're only using one side of this. Maybe the other side is going under maintenance. So we've got a single channel that we're looking at, and we're trying to remove particles, sand and some heavier particles, and we've established from looking at references and doing some lab tests that the downward settlement velocity is about 0.75 feet per second. That's a good benchmark for grit. Your mileage may vary, of course, depending on the size of what you're dealing with and what it's made up with. But for our example, we'll just assume that we've established that. We got a 5-foot deep basin with 4 feet of water in it. So we need to figure out how long it's going to take for that grit that's at the top of the channel coming in to settle to the bottom where we can collect it. And we can figure out, we figured out the settling time. We can figure out how long that's going to take pretty simply. Settling time is just the depth of the water, not the channel, divided by the settling rate. So we've got a 4 feet deep water. We got 0.75 feet per second settling rate. That gives us about 53 and change seconds for grit to settle out inside the tank. Of course, that means the basin has to be long enough for the particles to do that before the effluent stream gets out, because there is a horizontal flow velocity going on as well. We established in our last slide that 1 foot per second is kind of the ideal, but since things are going down and across the tank, they're actually settling in at sort of a diagonal. So we need to figure out whether our particles are settling out, our grit particles are settling out inside the tank or getting pushed along. And that's a relatively easy thing to do. We know what the velocity is here. We know what the time is we need to meet for particles to settle inside the tank, 53.3 seconds. So we can rearrange our velocity formula to determine the length or distance that they're likely to travel. At 1 foot per second times 53.3 seconds, they're going to go 53.3 feet on the outside. Of course, not every particle is at the top of the column when it comes in. Some are going to be lower, but this is kind of the outside edge. Of course, you can't randomly change the length of the basin, but if you had a 50-foot basin and you were running it at 1 foot per second with these parameters, and you were getting too much grit passing on into your primary settling tank, this would give you a clue as to what's going on. Maybe your water is going just a little bit too fast for your particular setup and you need to slow it down. Remember, when you're doing math, particularly on your obsert test, check your units just to make sure you've got the right math going on. So let's take this a step further and see how we might want to adjust the influent velocity of a tank to account for the specific length to see that it's doing what we need it to do. Because of course, unless you're designing, you can't just randomly change the length of the basin, at least not usually. So we can use the same formulas to figure out the maximum velocity for this particular tank, which again, 50 feet long, 4 feet deep. We know the settling time. We know the length. We're going to use the same formula. We've just got two different variables here. So instead of looking for length, we're looking for velocity. 50-foot tank divided by 53.3 seconds means our maximum velocity should be about 0.94, which theoretically at least means if we slow our velocity down a little bit by about 1/10 of a foot per second, most stuff should fall within that tank. So very basic math, but really useful. You can kind of model what's going on in your tank, or check what's going on in your tank based on your observations of things going right or wrong. So maybe you're doing this to figure out, what's going wrong. Ultimately, you got to figure out if that 0.9 feet per second is going to be effective, or if that's within the normal range. Fortunately, we can look these things up. As we said before, typical range for this is about 0.8 to 1.3. So at 0.94, we're probably within the right range. We might be able to slow it down even a little bit more. But as with all things, there's theory and practice. Something might not be designed quite right. Maybe it's not operating quite as intended. So you might have to make some process adjustments and do some other calculations to figure out what's going on. But some very simple math here can give you an idea of why grit might be ending up outside of your channel. Based on those results, you might realize, hey, the water's actually too deep. I need to run 2 channels at high flows and maybe only 1 at low flows. And you can use some observations in math to decide when you open both channels and run them at 2 feet, because if it's only 2 feet deep, it's going to take a lot less time for the solids to settle out, or what other options you might want to take. You could adjust the inflow. You might lower the water depth, like I said, by opening up another channel. Maybe, as we discussed in the last training, you have a flow equalization process as part of your preliminary treatment train. So maybe you can alter those flow equalization processes to dial in the velocity and volume of water going through your grit settling tanks. There may be other options. You might realize that you need to slow it down to keep the grit out of your preliminary tank or primary tanks, but that you are thereby going to trap some unwanted organics. But there may be a solution for that. Maybe you add a grit washing stage in between them so that you can then flush those organics back out and put them back into the wastewater stream. You might actually end up having to replace those channels with a cyclone. Who knows? A drastic change might be necessary for your system if it was designed for maybe a smaller population than you currently serve. My point here is not to give you sort of a definitive answer to solve the problem of excess grit showing up in your primary sedimentation tank, because there's a lot of reasons that could be happening. The point here is to show you that some basic math and observations and kind of an understanding of what's physically going on in that process can help you determine A, whether your system is operating within typical parameters or the specific design parameters for your system, and B, what impact prospective changes you might make are going to have on your operations, and whether they're likely to result in the results that you intend. So, what could work, what would be practical? Those are different questions that you kind of have to ask yourself. And if you've got a real basic channel like that, and you're wondering, how do I figure out what the flow velocity is? Quick and dirty method: throw a stick at one end, see how long it takes to do the other side, and use that formula V over dt. Just recognize that the actual average velocity is going to be a little bit slower than what you calculate typically, because things are going to move a little bit faster on the surface. So that's a very, very basic example. Of course, that's not the only kind of grit removal process. There are aerated grit chambers as well, where we're essentially I've engineered it so that the water is coming in at 90 degrees to the length of the basin, which is actually creating a spiral, which pushes our sediments to the bottom. We've also added air bubbles or aeration, which in turn makes actually lowers the specific gravity of the influent. An air-water mix has a slightly lower specific gravity. It's slightly less buoyant than water alone. And if you recall back to our regs and safety webinar, we talked about safety around activated sludge tanks, particularly the aerated portions of them, and the fact that if you fall into there, there's a very good chance you're going to sink to the bottom, because the aerated water has a lower specific gravity, even though you might float if the aeration sedimentation wasn't on. When it's on, you might think same thing's going on in this process, except instead of keeping everything moving, we're focusing on grit removal here by lowering the specific gravity over all of that air-water mix. It facilitates the dropping out of that heavier grit. Not going to show you any math for this particular instance, but just do want to show you that with slightly more complicated engineering, that gives us some additional parameters to play with. So if you were having issues with grit moving on here, you have the ability to both change the depth of the water, but also change the aeration as well. So, you know, you've got a mechanical action going on here. You've got a specific gravity action going on here. So you've got some additional variables to play with, but still you can use the basic math to kind of figure out whether things are working as they should. So that's a lot in 26 minutes. Let's do our first two poll questions just to make sure everybody's still awake. Our first one is related to where sedimentation is used in wastewater treatment. We'll give you about 30 seconds to answer this. Maya, if you wouldn't mind running the first poll.
Absolutely. The question is, where is sedimentation used in wastewater treatment? And the options are in the collection system, in preliminary treatment, in primary treatment, or in secondary treatment. All right, closing the poll in 3, 2, and 1.
All right, we got most of this right. So it's used in preliminary treatment for grit removal. It's used in primary treatment and secondary treatment as well to remove suspended solids. Typically not used in the collection system. It's actually kind of the opposite of what we want to happen. If you remember back to one of our earlier videos in the collection system design, we talked about scouring velocity and how collection systems are actually set up so that the effluent, at least at peak flows, runs through there and scours anything that's deposited inside the collection system out. Of course, there are probably some systems out there that maybe have some sedimentation basins out in the collection system, but that's atypical. So it's preliminary treatment, primary treatment, and secondary treatment. It's actually the opposite of what we want to typically go on in the collection system, because if things are there's a lot of settling going on in the collection system, that means things are getting plugged up and we're having to go in and clean them. Can we run the second poll question while we're here? And this is just a quick definition to remind you of what flocculation is. So is it breaking up big particles into small ones, gathering fine particles to form big ones, or discrete particle settling?
All right, closing the poll in 3, 2, and 1.
All right, almost everyone got this right. Yeah, it's gathering fine particles together to form larger particles. Discrete particle settling is really more sort of like the settling for sand and grit, kinds of settling where the particles aren't really interacting with each other. And breaking up of large particles into small particles is the exact opposite of what flocculation is. So we're basically trying to glom those tiny particles together so that they'll fall out a little bit quicker. But good job, everybody. So let's move on, now that we've done a very sort of simple example, to talking about sedimentation in primary treatment, so in primary settling basins. And this is going to take up sort of the bulk of the discussion. In primary clarifiers, they're designed to remove solids that are going to settle easily to the bottom or float to the top. But sedimentation is usually the principal basis of design for clarifiers. And what we're focusing on here are suspended solids. The reason we're trying to get those organic solids out in this phase is because they typically have a high BOD or biochemical oxygen demand on the receiving waters and the biological treatment units. We don't want to starve the bacteria that we're ranching in later stages. We don't want to overwhelm them either. So we use our preliminary or primary treatment to kind of dial in the BOD and solids that we want to move on to later stages. If a clarifier or primary settling tank is sized correctly, most of those lightweight particles with a specific gravity just above 1, so like 5, 10%, 15% higher than water, are going to settle to the bottom if the flow is slow enough. And typically here we're talking about flows in the 1 to 2 foot per minute range. Of course, the tank also has to be large enough for everything to settle out before it gets out, or most things to settle out. But in primary sedimentation, we're not trying to remove everything. We're just trying to remove the bulk of things. And we'll look at some typical removal rates here in a second. But because the specific gravity of the particles that we're dealing with in primary treatment, those organics, are so small, and because we're relying on flocculation, naturally occurring flocculation typically here, the settling rates are really, really slow. So let's use the same math that we used before to kind of analyze what's going on in a primary tank. In this case, we're looking at particles with very low specific gravity, maybe 0.05 and lower. So as I mentioned, they're going to have a much slower settling rate. Settling rate for particles in this size range is usually around 0.17 feet per minute or 0.0028 feet per second. And I want you to look at this closely, because when we were talking about grit removal, we were talking about 0.75 feet per second, which is actually 4.5 feet per minute settling speed, or settling rate. So we're an order of magnitude slower here. For our example, let's also assume a flow velocity of about 2 feet per minute. Again, much faster than we were talking about in the grit. Slower than we were talking about in the grit removal stage. There we were talking about 1 foot per second. Here we're talking typically 1 to 2 feet per minute in that range. And of course, we know the particle's moving horizontally and vertically, so it's settling in a diagonal. So again, just to reiterate, in this kind of settling, we're talking about minutes and hours, not seconds. Obviously settling rate, how long is it going to take to get from the bottom to the top? Let's assume we've got a 200-foot long channel with 10 feet of water in it. Exact same math, just some slightly different values. 10 feet deep, much slower settling rate. We're getting a settling time of 60 minutes. And this is actually on the quicker end of things. Again, order of magnitude different settling time, which means we, of course, then need an order of magnitude slower velocity and longer detention time, so that those things settle out in the tank where we want to, or at least enough of them to reduce the BOD level to where we want it to for our activated sludge process. So kind of begs the question, where in our 200-foot long tank are these sediments gonna land? Of course, some of them are heavier than this, because we're looking at a settling rate that accounts for the sort of slowest things. Some particles are larger and they're gonna settle faster, and some particles are gonna come in lower in the wastewater stream and they're gonna settle faster as well. Well, if we got a 200-foot tank and it's flowing at 2 feet per minute, and it's going to take 60 minutes for these to settle, everything should settle out in the first 120 feet, because 200 feet divided by 2 feet per minute gives us 100 minutes, or an hour and 40 minutes for water, theoretically, at least, to flow from one end to the other, assuming nothing is short-circuiting. We've established our settling time. Let's kind of look at this in cross-section. As I said, what's the distance traveled? Using the same formulas, velocity, length over time, rearrange that. Yeah, 2 feet per minute at 60 minutes. Everything should be settling out, or most of these particles that fall within the parameters we've established here should be falling out in the first 120 feet. And again, check your units. So what does this mean in practical terms? Well, if this is kind of a cross-section of our basin, most of the particles should be falling out in that first 60-minute time period within the first 120 feet. Of course, this is entirely theory. Not everything is going to happen like that. And again, in primary settling, we're not trying to capture everything. We're just trying to capture a lot. And what a lot means kind of depends on your particular process. So there are going to be, particulates settling out here as well. There's going to be some floating around up in here as we go along. But this kind of gives us a visual of what should be happening in our tank, assuming, again, we don't have short circuiting going on or weird currents in our tank that are getting in the way of our settling process. So, we know where stuff should be settling out. It kind of begs the next question of, well, how much of this is settling out? That's something you can check with lab tests, and particularly in larger utilities will be doing on the regular to look at your removal efficiencies. But there's actually an empirical formula that you can use. It's used for design purposes to get sort of a benchmark of what you can theoretically expect given a specific detention time. So as I mentioned, primary treatment, we're basically targeting BOD and TSS removal. Typically, in these processes, we're going to remove somewhere between 50 and 70% of the total suspended solids and about 25 to 40% of the BOD. Unfortunately, somebody has figured out an empirical formula that you can use to estimate what your removal efficiency should be based on a specific detention time in hours. And it's basically this, what you're looking at. Removal efficiency is just the time divided by a couple of empirical constants, one of which is multiplied again by the time in hours. Fortunately, there are tables available that tell us what those empirical constants are. So there are a different set of constants for BOD and TSS, but we use the exact same formula. So we can typically expect for a 2-hour detention time, plugging those numbers in. We should be getting somewhere around 56% removal rates for TSS, maybe around 35, 36% for BOD. And again, this is a formula that you can use to model what changes to your procedures impact might be. The example we talked about before with the tank, we had a detention time of 1 hour and 40 minutes, so 1.66 hours. So you're going to get a lower removal efficiency if you plug those numbers into these formulas. If you up this to 2.5, you would probably be up somewhere near the upper end of our removal efficiency parameters that we've got listed here over on the left. So again, another useful formula to know. This kind of thing can help you model what's going on in your system. Too much BOD, too much TSS is moving on into the activated sludge process. This is a quick and dirty way based on your existing detention times that you can figure out what's going on. Of course, you've got to also remember that detention times are going to vary because flows are going to vary over the day. So this is a calculation you might do a couple of different times a day or to evaluate flows at different rates. Been talking about detention time. So, settling tanks typically have a 2 to 3 hour detention time. It can vary depending on water quality and what's in your settlement, what needs to be settled out. They can be calculated using tank volume and flow rate. I'm not going to go into that here because we don't have enough time, and we did cover that in our Wastewater Math webinar. So if you are unclear about how to calculate detention times, I highly suggest you go back and look at that earlier webinar. It's explained very well, and there are a lot of examples in there. This is one of those places, again, flows vary over time, so operator experience really comes into play when you're running the plant because you're going to be dealing with increases and decreases in flows and increases and decreases in organic loads based on what's going on in the time of year. So for those of you who are new to wastewater operations, this really points out that you really need to talk to the people that you're working with and make sure you understand why you're doing what you're doing so that you can relate your operations to outcomes. And so that as you sort of progress in your career, you can look at a situation, evaluate it, and deal with it appropriately. Again, you can calculate theoretical detention times using tank volume and flow rate. You can look the formula up, recognize that you may want to verify that. Math is great, but what happens in practice is often a little bit different. But you can verify those calculations using things like floats and tracers and dyes. Realize that your actual detention times are often going to be shorter than the calculated theoretical time. If you're in a situation where you've got low detention times and your labs tests are showing really poor solids removal, again, you can sort of verify whether your lab tests and the math are jiving, and then you can start looking at solutions. Do you need to add tanks? Do you need to restrict flow to dissolve that detention time and solids removal process? Again, recognize their detention times are going to vary quite a bit between night and day. This is one of the reasons that some systems use the flow equalization techniques we talked about in the preliminary treatment webinar to sort of level out that curve, basically store and aerate some of that wastewater during the high flow times so that you can push it through at the low flow times and have more uniform detention times and flows. I've included a real simple design flow criteria table here. Not going to go through this now, but if you're looking at the slides, you can look at that as kind of a little bit of a reference. So one thing I left out of the tank that you probably noticed earlier is the outflow of our theoretical 200-foot tank. That's typically going to flow out through some weirs, and they're not always at the very end of the tank. Sometimes they are situated forward of the end wall to sort of facilitate the clear water coming in, which is again why we're trying to make sure that most of the particles that we're trying to focus on settle out in the front half of the tank, not the back half of the tank, because we want there to be at least up near the surface where water is coming across the weirs. We want the water to be relatively clear, or at least as clear as we want it. Obviously in primary treatment, it's not going to be as clean as it's going to be in secondary treatment. Of course, we don't want the water to go too fast either, because there is a flow going in here, and if that is too fast, it's actually going to suck pieces up from the bottom. But we'll talk about that in a second. Weirs more or less look like this. This is actually a secondary clarifier because I don't have a really good picture of a primary clarifier weir, but the principle is basically the same. You've got a trough that is collecting the water that's coming out of this particular process, and it's got a weir at the top with some notch teeth or something similar that is allowing the very top surface of the water to go in. And you can kind of see the difference in clarity between the water inside the trough and the water outside the trough. Some of that is because the water in the trough is a little bit shallower, but mostly it's because there's still a lot of solids suspended in here down at lower levels that you can see, whereas the water in the trough is much clearer. So how do we decide how much water should be going over this weir? How do we determine whether our sedimentation process is probably working right? Just like detention time is a parameter that we can look at and evaluate and compare to typical rates, there's something called the weir loading rate that we can use as well. And then just in case you weren't sure what's what, that's the basin, that's the trough, that's the weir. The weir loading rate is essentially just the linear feet of weir that water's flowing over relative to the flow over the course of a day. And it's really important to understand what that rate is to make sure you're in operating parameters and you're not short-circuiting your operation or your basin. And by short-circuiting, I basically mean creating areas where there's really high velocities near the weir that might actually pull solids out and into the next process that you don't want to. So it's a normalized value. It's the number of linear feet of weir in the clarifier in relation to flow. So it's the flow divided by the feet. And we talk about it in terms of volume of flow over 1 linear foot of weir per day. I'll show you how to calculate it in a minute, but typical design parameters are typically between 10,000 and 20,000 gallons per day per foot of weir. Could be higher for fast settling solids or intermediate treatment where you're not trying to remove as much of the solids from the stream, but in secondary clarifiers, and particularly if you want to have higher quality water, you're going to have relatively low weir loading rates, maybe even below that 10,000. So how do we calculate that? Again, really simple formula. It's the flow divided by the length of the weir. What you've got to remember is it's the flow in gallons per day. So on an exam, you might be given something where it gives you 5 mgd. You need to convert that into gallons before you do this. Otherwise, you're going to come up with a number that is wrong. And then, of course, you have to calculate the length of the weir, which is going to depend entirely upon the design of the basin. So, if it's rectangular, it's going to be one or more widths of the basin. If it's circular, you're going to have to use pi times diameter to figure out the circumference of that weir. And again, it's really important. It's not the circumference of the basin, it's the circumference of the weir. As you might recall from our picture, the weir is typically sitting right inside the basin. There are some different designs, some are actually on the outside, but that's something particularly to pay attention to when you're doing these calculations. So let's do a quick loading rate example just to kind of give you an idea of how you might calculate this. Imagine we've got a circular clarifier. The weir is 75 feet in diameter, and we've got 5 million gallons per day flowing through this thing. So since it's a circular weir, we've got to figure out what the diameter is, because again, we want the linear length of a weir. So that's pi times the diameter, 3.149 times 75 gives us roughly 236 feet. We get a weir loading rate by simply dividing our flow in gallons per day by that linear feet. That gives us here a value of 21,170. I've got that in yellow because it's just a little bit outside typical design parameters. It might be a problem, it might not. Again, if this were on a test, I would probably say it's outside of design parameters. In the real world, it might be just fine. It's 6% outside the typical range, but you might also have relatively low solids concentration, so that higher weir loading rate might be okay. It's really going to depend on the situation as to what's acceptable and on what you're observing and seeing in test results of the effluent that's coming out of here, the clarified effluent that's coming out of here. So going back to our secondary clarifier here, imagine this, because this is one design. Sometimes there's a single weir. This happens to be a double weir. So if we think about the calculation I just did, I only accounted for about half of the weir here, because there's two, there's one on either side. So again, in the rectangular example, I showed multiple weirs. A lot of times there are going to be more than one. A small system might only have a single weir, but a large basin may have multiple weirs. So you need to take that into account. Here's a simple way to do that. I've got, 2 weirs here, 170 feet in diameter, 175, just add them together, come up with the now significantly larger length, do my math, and now I've got a weir loading rate of just under 11,000 GPD per foot, which is well within the normal design parameters. So again, sometimes things look weird because you did the math wrong, so that's something you need to look at. There is also the surface loading rate. Again, I'm not going to go into depth with this because this is something that was covered in that Wastewater Math webinar that we did a while back. But this is just another relationship. It's GPD per square foot of clarifier surface area. It's another metric that we can look at to sort of evaluate whether our performance is correct or if we're having problems. This is math we can run to see if where the problem might lie. And it's simply the flow divided by the surface area. So it's a slightly different way of looking at how fast water is moving through the basin, which of course then is going to impact the settling action that's going on in that basin. So we got about 12 minutes left. Let's switch gears here and talk a little bit about some things that impact sedimentation. Then I'm going to do a short little blurb on secondary clarifiers and what's going on there, because it's essentially more of the same, just more complicated because we've got flocculation going on there. But since we're talking about things, sedimentation and things that can go wrong, I want to talk about a few things that you really need to be aware of as you start. One is that temperature can have fairly significant impacts on sedimentation processes, particularly if you're in an area that has very big seasonal temperature swings, or drastic temperature swings, or if you've worked at a plant in Arizona for a long time and you move to Michigan in the wintertime and you wonder why everything is taking a lot longer, this is why. Water changes density a little bit and becomes more viscous as it gets colder. The warmer the water is, the less viscous it is. And although these images are obviously grossly exaggerated for the visual, what it kind of demonstrates is that when water is warm, the molecules are a little bit farther apart. They don't stick together quite as well, and particles can travel through them a little bit faster. The colder the water gets, the more that is inhibited, of course, assuming it's not entirely frozen, because then nothing's going to be moving through it. So, temperature can have just an overall effect on the rapidity of settling processes and biological processes as well, but that's a discussion for another day. There's also the issue of short circuiting, which I kind of referred to earlier, but I want to show you sort of specifically what that is. Short circuiting is when water in the tank isn't being evenly dispersed across the area, and that results in velocity gradients where the water is moving much faster in part of the tank than it is in the other. So imagine we've got a rectangular tank here. We've got the flow coming in the lower left. It's going out at the lower right. We've got some baffles. That's what those black lines are, or rear plates or port openings, depending on the design of your particular tank. And if it's designed badly or not operated correctly, you can end up with a flow pattern that looks something like this, where you've essentially got two different velocity gradients going on. You've got a high velocity area up near the top here, but because of the way the water is flowing through, you end up with a low velocity area at the bottom. What this results in is a phenomenon called short circuiting, basically meaning in those high velocity areas, the water is moving through much faster than it's supposed to. In other words, the detention time of the water moving through that area is lower than what you want, and you're probably pulling a lot of the particulate along with it that you want to actually settle in the tank. Conversely, in that low velocity area, the detention time is increased, and that can be a real problem, particularly in the primary treatment, because your influent there might become septic, it might develop odors. So, good design and good operation is really key to avoiding short circuiting. That's why these things have weirs and baffles and port openings in them. And when the designers really pay special attention to inlet design to make sure that the flow is even, so that what's happening on one side of the tank is the same thing more or less that's going on the other side of the tank. So again, high velocity areas reduce the detention time, low velocity areas increase the detention time, and that can cause problems. There are other kinds of short circuiting that can happen due to temperature stratification in the actual tank. So before we were looking top down, now we're looking at a cross view of a tank. So if you've ever been swimming in a lake, particularly like early in the summer, you're swimming along at the top and the water's relatively warm, and then you go to stand up and you're freezing from the knees down. And that's because cold water is denser, it sinks to the bottom, the warm water tends to float on top. And there can be a temperature differential between the effluent coming into the basin and the water that is already in the basin. So if we've got a situation where the basin is cold and the influent is very warm, and it's typically not ice cold because it's got biological things going on in it, what can end up happening is that the influent kind of flows along the top, doesn't mix throughout, and as a result, you end up with a short circuit at the top and septic conditions at the bottom of the tank. Again, in the high velocity area, you've got a reduced detention time. In the low velocity area, you've got an increased detention time. And, particularly in primary treatment, this can be problematic because if it's septic down there, things are decomposing, bubbles might form that might actually start raising sludge up and causing all sorts of problems. Of course, the reverse can happen as well. Depending, if we've got a situation opposite here where the basin's warm and the influent's very cold for some reason, you might get a travel path that looks something like this, where the cold influent is kind of sinking to the bottom and then moving out. And basically it's the same issue, just reversed. You've got low velocity at the top, you've got higher velocity at the bottom. And as a result, you can get septic conditions. And of course, since at the top, whatever smells are developed are going to be out for your customers to complain about. So these are things that you really want to pay attention to. having high velocity areas at the bottom can be really problematic because, we talked about in the collection system, we design things to have scour velocity so that things don't stay in the pipes. Well, in the tanks, we don't want scouring velocity because we want the particulates that settle to the bottom to stay in the tank. Scouring velocity is kind of complicated. It kind of depends on a lot of things, the size of the particles, their specific gravity, friction factors, particle cohesion. I've got an example here just to show you for a particular primary tank. The scouring velocity in this particular tank would be about 12.4 feet per minute. So assuming that things were operating as normal and there wasn't any significant short circuiting going on and you weren't really, just shoving water through here, this shouldn't happen because, the tank's designed typically to run between 1 and 2.5 feet per minute. Scouring velocity is probably not going to be an issue, but this is something you should look into, particularly for upper level certification tests, because you may need to know this and be able to calculate it. But again, in your actual operations, unless the plant was really badly designed or you're operating way outside of normal parameters, this probably isn't going to be too much of an issue, but there is a formula you can use and tables that you can use to look up and check it just to be sure. Again, doing that mathematical modeling to see whether you've got a significant problem. Actually, I'm going to skip this last poll question in the interest of time because we're running a little bit slow, and I did want to give a short amount of time to secondary treatment. Physically, this is kind of more of the same. We're talking about, gravity settling. The difference here is that we're hopefully getting much more clarified effluent. We are looking at least initially, higher suspended solids concentrations coming into the tank than we would necessarily see in a primary tank. And we've got, again, some fancy engineering that is helping us and particularly helping that flocculation, whether it's naturally occurring or whether we're supplementing it with polymers and additives to make sure that that is occurring in the tank where we want it to. And then, of course, we've also going to be dealing with flotation in our secondary clarification processes. So there's a lot of different designs. There's rectangular tanks, there's center feed tanks, there's rim feed tanks. There's a lot of different kind of sludge collection methods, but they're all kind of using the same principles, just different design methods. I'm going to show you a circular version to talk about this. And the reason that we're trying to get all of the solids out of the effluent in the secondary clarification process is because that's got a lot of bacteria in it, and there's not really any food left at this point. So we want to get the microbes back out of here and back into the activated sludge tanks where there's food so that they can do their job. And we use our secondary clarifier to do this. And you can kind of see the effectiveness of these by just looking at this inner ring, this inner ring and how dark the effluent is there versus the outer ring and how clear it is. You can actually see those fish in there. Basically what we're looking at here is kind of a flocculation well type situation where we've got a ring in the middle, the effluent is coming up through the center, and it is going through an influent port that has some diffusion baffles inside that dissipate the energy of the influent, that mixed liquor that has fairly high solids concentration. And that ring, that inner ring that we're looking at actually extends down probably halfway to the bottom of the tank. And the idea is we are promoting flocculation in there by sort of corralling these solids in there and forcing them to bump together as they work their way down and out into the rest of the tank. They're basically combined in there, they bump together, they flocculate, they coalesce, they get greater mass, and they sink to the bottom. And of course, there's scrapers at the bottom of this tank. We've shown you in past videos the sort of cross sections of these. There's scrapers at the bottom pulling the sludge together. And the reason we've got that ring in there is to ensure that most of the larger particulates and microbes and everything else in there that we want to get out is falling out in that sort of center cone of the tank. And then, of course, we've also got a weir at the end. We've got the center well there, and we've got that scum baffle running around the edge and our skimmer as well, which brings us to a very short discussion of flotation. Typically, you're going to see this, in secondary clarifiers. they're almost, I don't never seen one that didn't have a scum baffle on the top, but that stuff up there is scum. That's, leftover things, some stuff that gets blown in, little bits and pieces that haven't been trapped earlier, that have, again, very, very low specific gravity, lower than 1, so they're buoyant and they float. There could also, there can be a variety of things in there. And we've got a scum baffle that is between the weir and the center of the tank. It's usually only a few inches deep because we're basically just trying to capture stuff on the surface. And then we've got our skimmer arm that is very, very slowly moving its way around the surface, capturing all of that guck that's floating on the top and pushing it off into a tray. So quick and dirty discussion of sedimentation and flotation and flocculation as it applies to some basic wastewater treatment processes. Again, my goal here wasn't to do a definitive education on all of the pieces, but to kind of give you some basic formulas and information that you can use both on the test and to sort of check facility performance. You can use surface loading rates, rear loading rates, removal efficiency, detention time formulas, to compare to common design values or the specific design values for your particular system. These are always going to be used in combination with lab tests and process controls, obviously, but used together, they can really help to verify that your operational goals are being achieved. If you're getting lab samples and they're not what they should be, you can go back to some of this math and your understanding of physically what's going on in the tank, and use that understanding to kind of assess performance and look for problems. And again, if lab tests show poor performance, because that's typically where you're first going to notice it, the math tests can help you identify where the operational problems are happening, because of course you're going to be sampling throughout your process. So again, quick and dirty, I went 1 minute over. I'll open the floor to questions. I do want to point out that if you have something here that sparks your interest that you want to talk to us about, whether it's test related or related to your specific plant, and you want to think about, talk about some possible solutions or brainstorm, we have regular office hours every Tuesday from 10 to 11 Mountain Daylight Time, which is obviously different in other time zones. We've got them listed here. You can reach out to us by email. AJ and my emails are there. I've got a fairly good theoretical knowledge. AJ worked in the Albuquerque plant for years and has a whole lot of practical knowledge. Between the two of us, we should be able to help you. And if we can't figure it out, we'll find somebody who can. So with that, I'll throw our contact info up there, our website up there. The EFCN network site has our past webinars. If some of the things that I mentioned but didn't cover in this spark your interest, please go back and review those webinars. And again, these are our introductions, they're supplements, they're not the only things that you should be studying. I highly recommend the Sacramento State Water Programs books, particularly if you're just getting started. They can be a bit dense at time, but they cover a lot of material and have sample questions and things like that in them. So with that, open the floor to questions if we have any.
There is at least,
Sorry, go ahead. I'm sorry.
I see the first one is asking about if fishes are used for treatment, and is it harmful for them, the wastewater? James, do you want to answer that, or do you want?
Yeah, actually, it's very interesting. I threw those pictures in there just for fun. We're actually going to be putting out an educational video on these. Those are from a particular plant down in Texas. They started out with about 250 koi in each of their secondary clarifiers, and it actually pretty drastically improved their water quality. Typically, it's not going to be a problem. Obviously, your mileage may vary. It kind of depends. I'm not going to suggest that you just throw fish in every clarifier, but it can work. There's a fair amount of literature about this out there available, and if somebody's interested and wants to reach out to us, we can point you at some of the articles. But basically, they work around in there and eat remaining suspended solids and don't really poop out much, and what they do poop out settles to the bottom very quickly. From the few systems that we've seen that actually are using fish, they've had a net benefit from doing that. Obviously, there's different kinds of fish, and in this particular situation, this process is entirely self-sustaining. They don't feed the fish. When one occasionally jumps out, obviously they put it in the garbage can. The only thing that they have to worry about is during spawning season, you get, for a very short period of time, a lot of fish eggs in there that you have to deal with. So that adds a slight operational wrinkle, something you have to watch out for. But this particular facility, they were having issues with too many solids coming through at their secondary clarification facilities, and they talked to some neighboring systems and to a fish farm, bought some fish, threw them in, and it worked out fine. And the regulators in Texas don't have any problem with this. Of course, again, that's a your mileage may vary kind of situation, but it's definitely something worth looking into. And oddly enough, it's kind of turned their clarifiers into something of a park. People actually come by and go on tours specifically to see the fish. So somewhat long-winded answer, but generally there's not a downside.
There's one question that's talking about 3.14. They might be referencing pi. I'm not really sure what that question was about. That's the only other question we have on here.
Yeah, pi. So the value of pi, if you're calculating, circumference or the area of a circle, you have to use pi as part of that calculation, which is that little sort of Stonehenge-looking symbol. That's a Greek symbol. Mathematically, it's a non-ending number, but for tests, you can usually use 3.149, and that's a good enough abbreviation that'll get you close enough to the right answer for any test and any work you're doing here. So that's all that was. It's just the actual numerical value of the symbol pi.
Someone also mentioned, I think this is worth noting as well, that you got to be careful that the species that, if you do use a species like query, that they're not an invasive species.
Yes.
That, or also use sterilized fish.
Right. Yeah. That's those are two very good points. Particularly if you are using a situation where your disinfection is not using chlorine, these guys got to have a fail-safe in that they use chlorine disinfection. And on the very rare occasion that a fish gets out into the chlorine race, the chlorine levels are so high that they just kill it instantly. And I actually did see one fish a couple of years ago when I was visiting in the chlorine race. But yeah, that is a very good point. You don't want to be responsible for reducing or introducing invasive species. You've got to make sure that whatever you add, you can control. So yeah, very, very good point. I'm glad somebody brought that up. And again, if you're thinking about putting fish in, don't just do it willy-nilly. You don't want to just take your kid's goldfish and throw it in there. Like everything else, should be a well thought out process, and you should do some investigation and some research before you jump into something like that. All right. Well, I think that's it. I appreciate everybody staying over a little bit. I do realize that, with the Q&A session, we ran over by about 10 minutes. Again, if you've got other things that you have questions about or want to address, not necessarily related to sedimentation, there's a whole host of wastewater issues out there. The grant that provides the funding for these webinars and the training sessions we have also provides for technical assistance. If we can't help you, we can typically find a service provider who can. So please do reach out to us. It's your tax money at work. The Fed's already got your money. They're handing it out for training and technical assistance. So take advantage of it, please. It's interesting to us and it keeps us working, and hopefully we can do some good. So with that, I'll give you back the rest of your day. Thank you for attending. This is an ongoing series, so there will be additional ones advertised. And again, if you ever have any questions, please reach out to us. We're happy to help.
All right. Thank you, James and AJ, for sharing your expertise with us today. following this webinar, you will receive an email with the slides from today and a link to the recording. We also ask that you complete the webinar evaluation following the webinar so you can let us know your thoughts on today's session, as this helps us plan future webinars on topics important to you. Thank you all again, and we hope to see you at future EFCN events.